This is a video about matrices, and we're going to talk about the determinant. So the previous video to this talked about identities, and so you should know everything up to here, which is the basics, the addition, subtraction, scalar multiplication, matrix multiplication, and identity. And now we're talking about the determinant. Now with determinant, we only use determinant with square matrices. So the determinant of a square matrix tells us whether or not the matrix has an inverse. And we're going to talk more about inverses in the next video, but right now we're going to talk about the determinant, and then in the next video when we talk about inverses, we'll put the determinant in context. But we need to know how to get the determinant, and we'll find out what it's useful for in the next video. So let's start with a 2 by 2 matrix because we're only dealing with square matrices. So let's say that our 2 by 2 matrix we call A has elements little a, b, c, and d. So these can be any values. They can be positive, they can be negative, they can be zero, they can be fractions, they can be any value in there. The A, B, C, D is just telling us the position. So A is row 1, column 1, B is row 1, column 2, etc. The determinant of A, which is our matrix, is simply A times D, so it's whatever value is there multiplied by whatever value is there, minus B times C, so the product of those two. So it's the product of that diagonal minus the product of that diagonal. And that's all the determinant is. So if we have a look at a matrix, remember it has to be a square matrix and we're dealing with 2 by 2s at the moment. So let's do 4, negative 1, 5, 0. Let's not do 0 actually, let's do 2. So I'm just going to press enter so that it's there and we can see it. Now let's think about what the determinant is. It's the left to right diagonal product, which means multiply them, minus the right to left diagonal product, which is multiplying them. So in this case it would be 4 times 2 minus negative 1 times 5. So 4 times 2 is 8. Negative 1 times 5 is negative 5. 8 take away negative 5 is 13. And you'll notice on the calculator that for multiplying, it does that little dot. So if we press the multiplication symbol, it does the little dot. So 4 times, it does the dot. So don't be confused if you think that's 4.2 take away negative 1.5. It's 4 times 2 take away negative 1 times 5. So 8 take away negative 5 is 8 plus 5, which is 13. So we've determined that the determinant of this 2 by 2 matrix is 13. The calculator can also do this. If you go to the matrix menu and you have a look at number 3, so that's menu 7.3, it says determinant. We can actually put that matrix into that formula and it'll give us the determinant. So remember, we could have defined that matrix. We could have put that matrix and stored it as matrix A. That's something we can do. And then we could have just typed det. Now remember, once it's italics, it means it's not anything. As soon as it's not italics, it means it's something. And we can put A there, and it will use that matrix to work out the determinant, which is 13. So we can do it calculating it. You could do it in your head or on the calculator. You could do it by going menu 7.3, which is determinant, or you can just write det bracket and then put the matrix in. And that will get you the determinant. Now the determinant is used, it says here, to tell us whether or not the matrix has an inverse. And the only thing we're worried about is if the determinant equals 0. So if you have a look at this highlighted box here, if the determinant of A equals 0, then the inverse of A does not exist. So the opposite of that is also true. If the determinant of A does not equal 0, then the inverse of A does exist. So this is critical for the next thing we're going to do. If determinant of A equals 0, then the inverse of A does not exist. So looking at our matrix that we did before, we can see, because we know that the determinant of this is 13, we therefore know that this matrix here does have an inverse because the determinant is not 0. Therefore, that original matrix does have an inverse. If it did equal 0, then it would not have an inverse. And I'll do a matrix now that has a determinant equal to 0. So we're doing a square matrix, 2 by 2, 3, negative 1. Let's do 6, negative 2. And this matrix here, if we check the determinant, we will work out that it has a determinant of 0. And now the reason I knew this would have a determinant of 0 is because I made it so that the diagonals, when we multiply them, equal the same thing. So 3 times negative 2 is negative 6, negative 1 times 6 is negative 6. So if they equal the same thing, when you minus them, you're going to get 0. So that's why I chose that matrix. So all we know now by using the determinant is that this matrix here, 4, negative 1, 5, 2, does have an inverse because its determinant was not 0. We also know that this matrix here, 3, negative 1, 6, negative 2, does not have an inverse simply because the determinant equals 0. So that's what the determinant does. It determines whether a matrix has an inverse or not. If the determinant equals 0, that matrix does not have an inverse. If the determinant does not equal 0, then it does have an inverse. What it equals in this step is irrelevant. It's just whether it equals 0 or not. The fact that it's 13 will be used when we're finding the inverse, which we'll do in the next video. But for now, the fact that it's 13 is irrelevant. It's just relevant that it's not 0. Not 0, inverse does exist. 0, inverse does not exist. And if we have a look back at the summary, a singular matrix is a matrix that has a determinant of 0. A singular matrix is one with a determinant of 0. So going back here, we would say that this matrix here is singular. This matrix here is not singular. So in matrices, the term singular purely refers to whether the determinant is 0 or not. If the determinant is 0, the matrix is singular, which means that the inverse does not exist. If the determinant is not 0, then the matrix is not singular, which means the inverse exists.